The diagram shows the axis of coordinate system S at rest relative to the Earth. Earth is at origin of S. X prime and CD prime are the coordinates of reference frame S prime in which spacecraft is at rest. When the origins of these two sets of axes coincide, all clocks in the frame show zero. So the speed of spacecraft is 0.80 c as measured in s. So asking you what is the speed with which the spacecraft is moving. So since this frame ct prime and x prime is off the spacecraft and the angle theta subtended over here can help us to find the speed with which this spacecraft is moving. So what is the formula? So we know that tan theta is equals to v over c. V will be c times tan theta. By plugging the value of tan theta, what is tan theta? It's opposite. This is your opposite, which is 4 light year, divided by adjacent, which is 5 light year. You will get the answer as 0.80 c. Next, an event has coordinate x is equal to 0, and ct is this with respect to s frame. Show using Lorentz transformation that the time coordinate of this event in s prime is ct prime. Now I'm going to use this Lorentz transformation, which is given as ct prime is equal to gamma times ct minus vx over c. The value of x is 0. That makes ct prime equals gamma times ct. The value of ct is given as 0.60 light year, but what's the value of gamma? So we'll calculate the value of gamma separately. The formula for gamma is 1 over root over of 1 minus v square over c square. That is 1 over 1 minus, what is the value of v, which is the speed with which the spacecraft is moving. That is 0.80 square c square over c square. And if you simplify this, the value of gamma will be 1.67. I'm going to substitute the value of gamma here, which is 1.67 times the value of ct, 0.60 light year. That will give me 1.00 light year. Next, label on the diagram with letter P the point on ct prime axis whose ct coordinate is 1 light year. Okay. So since we calculated CT prime coordinate as 1 light year, they're asking you to label that point P onto the CT prime axis. I mean, you can't just randomly say this as 1 light year, right? You have to accurately locate it. So how do you do this? Before that, I just want to touch a small fundamentals in math. For example, if this is how our x-axis and y-axis are, and there is an event E here, which has the coordinate x comma y. If I ask you locate this event E on x-axis, you will draw a line parallel to y-axis. If I ask you locate this event E on y-axis, you will draw a line parallel to x-axis, right? So using the same logic, since we know that 1 light year on CT prime is 0.60 light year on our rest frame. So this is your 0.60 light year on your rest frame, and you have to locate this coordinate on CT prime. So since I'm locating this coordinate on CT prime, I will, which is your y-axis for S prime, you will draw a line parallel to your x-axis of S prime and see where that line intersects the CT prime. So let's do it. I'm going to draw a line parallel to my x prime. As you can see, that line is parallel to my x prime, and this is where it intersects, and that is my point P. Basically the coordinate 1.00 light year. Next, at CT equals 0, a light beam is sent from Earth to space station at rest 4 light years away in S. Basically, space station is 4 light years away with respect to the rest frame S. Event R is the arrival of light beam at space station. Draw lines to indicate R on the diagram. So first of all, I'm going to draw a world line for the light. So, which is at an angle 45 degrees with both x-axis and y-axis. Next, I'm going to draw a vertical line, drop a vertical line from 4 light years onto this light world line, photon world line, and that's going to be my event R. That's going to be my event R. Next, determine using the diagram or otherwise the space coordinate x prime of event R in S prime. So they're asking you what is the coordinate of x prime? Means since the coordinate of r on x is 4 light year, what is the coordinate on x prime axis for the same event r? Now, since we wanted the coordinate on my x-axis, I will draw a line parallel to my y-axis. So look at this. I'm drawing a line parallel to my y-axis and see where it intersects. That's the point where it intersects, right? And that's going to be my, let me label it as r prime. Fine. Or maybe you can also use a Lorentz transformation to locate this coordinate. So what is the Lorentz transformation equation? X prime is equals to gamma times x minus vt. The value of gamma, which was calculated previously as 1.67, and x is 4 light year, minus speed with which it is moving, the spacecraft is moving, is 0.80 c times value of t is 4 light year. And if you, wait, don't forget, this value of v is 0.80 c, but the t is 4 light years divided by c, because this CT value is 4 light year, but we wanted the value of t there, which is 4 light year divided by c. And this c gets cancelled. And if you simplify this, the value of x prime is 1.33 light year. A muon is an unstable particle with a half-life of 0.56 microsecond, as measured in the Mons rest frame. So this time period is with respect to a clock that is at the rest frame. For example, if this is a muon frame, there's a clock inside the muon, right? And that is measuring this time period of 1.56 microsecond, right? And what if someone else is measuring this time? Obviously, the time period with respect to that frame will not be same as the time measured with respect to the muon frame. Why? Because this clock is moving along with the muon, and with respect to any other frame outside, let me call this as a rest frame S, the clock is also moving close to the speed of light, and which will cause it to have a time dilation, right? Anyway, so I want to just make it very clear here. This time period is with respect to a rest frame, that is muon's frame. Muons are produced in a laboratory and are all directed at speed of this much. So that's the speed of the muon, 866C towards the muon detector. The gamma factor for the speed, okay, so gamma is already given. You don't need to calculate it. The detector, according to the observer in the laboratory, is at distance d from the muon source. So this distance d is measured with respect to the rest frame detector. But this distance d may not be this distance d for any other, with respect to any other frame that is moving with some speed of close to the speed of light because of the relativistic effect called length contraction. Moving on. According to a laboratory observer, the number of muons detected to the number of muons produced is 1 by 2. That means if 100 muons have been sent from the muon source, only 50 of them is reaching. So that's basically half time, right? Half life. I should not use the word half time, it's half life. So yeah, the question is calculate the value of d. So distance d is speed into time. So what is the speed with which the muon is moving? 8.866 c. And what is the time it takes to reach the detector? Now, you may say the time to reach the detector is 1.56 microsecond, but don't forget that time is with respect to the clock inside the muon, right? But we're talking about the distance d with respect to the detector. That means how long does it take for the muon to reach the detector? That means the time period with respect to a rest frame. So that will cause time dilation. So what will be the formula for time dilation? T will be gamma times the proper time period, right? So which is 2 times 1.56 microsecond. And if you solve this, your answer will be 811 meters. Next, in the muon's source, rest frame S, the detector is approaching at a speed this, obviously, right? Because if you consider the detector to be a rest frame, the muon particles are moving towards the detector with the speed equals 0.866 c. Whereas if you consider the muon particles to be the rest frame, that means with respect to them, the detector is approaching them, right? Fine. So, question number one, show that the distance traveled by the detector when it meets the muon source is 405 meter. Now, since we already calculated the distance traveled by, distance d with respect to the rest frame is 811 meters, but now this detector is moving. Previously, when I solved the previous question, the detector was assumed to be the rest frame and muon particles are moving. Now this time, muon particles are considered to be rest frame, but as detector is moving towards it, right? That means there will be a relativistic effect seen by the detector because it is moving close to the speed of light, and therefore this will cause the length contraction, right? By how much factor? Gamma factor. So what will be the distance traveled by the detector? It will not be 811 meter because it is not at rest anymore. It is moving with speed close to the speed of light that is given here as 0.866 c. Therefore, the distance will be half the 811 meters because, and why half? Because the gamma factor is 2, so it will be divided by 2. So which is going to be 405.5, which is approximately 405 meters. Next, determine the time taken for the detector to reach the muon source. The time it takes to reach the muon source will be the distance it travels divided by the speed with which it's traveling. The distance traveled is 405 meters. Divided by the speed with which it is traveling is 0.866 c. When you plug in all the values, the answer is going to be 1.56 microseconds. Next, calculate using the answers to B1 and B2 the ratio of number of muons ejected to the number of muons produced in S. Now, since we found that the time taken for the detector to reach the muon is 1.56 seconds, which is equal to the half-life of muons, that means the ratio of muon detected to the muon produced will be half. Next, comment on the ratios in A and C. As you can see, the ratio that was given in A was 1 by 2, and the ratio that we've calculated here is also 1 by 2, which says that the ratios are same no matter whether it is whether the detector was considered to be the rest frame and muon considered to be the moving frame, or vice versa, because the count rate remains same with respect to any frame. Star A and star B are separated by a fixed distance of 4.8 light years. So the distance between star A and star B is 4.8 light years, and this distance is in the reference frame in which they are stationary. So that means with respect to some stationary frame, these two are stars are distance of 4.8 light year. But remember this distance may not be same with respect to any other frame which is moving. For example, in the diagram, you can see the space station is moving with a speed close to the speed of light. The shuttle is also moving very close to the speed of light. That means these two objects will not see the distance between star A and star B as 4.8 light year. They will see slightly lesser than that. By how much lesser? By factor of gamma. Proceed. An observer P at rest in the space station moves to the right with speed 0.78 c related to the stars. A shuttle S travels from star A to star B at a speed this related to the stars. Right. So what is the speed of this object? I'm considering the shuttle to be an object and this frame to be a stationary frame S and space station to be a moving frame S prime. So with respect to the stationary frame S, the speed of the object U is 0.30 c, whereas the speed of the same object shuttle with respect to S prime is not given, but let me call it as U prime, which is a question mark for us, right? Now, what is that 0.78 c? It is the speed with which the space station is moving. That is represented with the letter V, which is 0.78 c. Now, state the value of the maximum distance between the stars that can be measured in any reference frame. So they're asking what is the maximum distance between the stars that can be measured with respect to any reference frame. Obviously, I've clearly said that this 4.8 light year is with respect to the rest frame, but it will be shorter for any other frame which is moving closer to the speed of light. So answer is 4.8 light year. This is the maximum distance that can be measured by, obviously, by a stationary frame. Next, write down the speed of shuttle S relative to observer P using Galilean relativity. Perfect. So you have to be very careful whether they're asking the speed of anything with respect to Galilean relativity or with respect to Einstein's relativity, right? So what is the formula for Galilean relativity? U prime is U minus V. So what is the value of U? It is 0.30 C, whereas V is 0.78 C. So if you simplify this, your answer is going to be negative 0.48 C. So what does negative states? It states that with respect to the observer P, the shuttle is moving back with a speed of 0.48 C. Next, calculate the distance between the star A and star B related to observer P. They're asking what is the distance with respect to the observer P. So as I clearly said, the distance 4.8 light year is only with respect to the stationary frame, but it will be shorter for any other frame. to calculate that length with any other frame, you have to calculate the gamma for that particular frame. So the question is to calculate what is the distance measured by the observer P. So let's calculate the gamma factor for this observer, which will be 1 over root of 1 minus v square over c square. The value of v is 0.78 c. So if you plug in over there, your answer of gamma will be 1.6. Now, since we got the value of gamma, what will be the length between star A and star B measured with respect to the observer? It will be the proper length divided by the gamma factor. The proper length is 4.8 light years divided by the gamma factor is 1.6. Now, I just wanted to remind you that proper length is nothing but the length measured by a rest frame with respect to a rest frame. And if you simplify this, your answer is going to be 3 light year. Next. Show that the speed of the shuttle S relative to observer P is 0.6 c. So, sir, we have already calculated the speed of the shuttle here, but that was using Galilean relativity. But now they're asking you to calculate with respect to Einstein's relativity. So, what's the formula for U prime? So, U prime is U minus V over 1 minus UV over C squared. You don't have to worry, this formula is there in your data booklet. You can use that. Now, the value of U, which is the object velocity with respect to the rest frame is 0.30 c minus v, which is the observer velocity 0.78 c divided by 1 minus 0.30 c times 0.78 c divided by c square. And if you simplify this, your answer is going to be negative 0.63 c. And again, the negative stands for that the shuttle is moving back with respect to the observer P. But as you can clearly see here, with respect to Galilean relativity, found it to be 0.48 c, but with respect to the Einstein relativity, it is 0.63 c. And as we know that there are a lot of other evidences that proves that yes, Einstein relativity is more accurate compared to the Galilean relativity for an object moving with speed close to the speed of light. Next, calculate the time according to observer P that the shuttle S takes to travel from star A to star B. So, according to Lorentz transformation equation, that is T prime equals gamma into T minus Vx over C squared. This is there in your data booklet. The value of gamma is already given, which is when it has already been calculated above, which is 1.6 times what is the value of T? That's actual time. That's the proper time. That means the time taken by the space shuttle with respect to its own frame, right? Or with respect to a rest frame. So what is the time taken by the space shuttle? So proper time will be the actual distance, which is 4.8 light years divided by distance by speed, which is 0.30 c minus v stands for speed of the spacecraft, which is 0.78 c times the value of x, which is the actual distance again, right? That's x stands for the actual distance, which is 4.8 light year divided by c square. And if you simplify this, your t prime will be around 19 years. Next, identify and explain the reference frame in which the proper time, underline that, in which the proper time for shuttle S, the journey from star A to star B can be measured. The proper time is nothing but, if you have to define the proper time interval, it is the time between two events that takes place at the same point in space. So if I have to measure like proper time, so let's say this is my space shuttle and there is a clock inside it, and that's the star A, that's a time t1. And when it reaches the star B, the clock measures another time, say t2. The difference between that will be the proper time because the clock is there within the shuttle, right? The clock is not moving. I mean, what is the speed of the clock with respect to the shuttle itself? The speed of the clock with respect to shuttle is zero. So that means it is a it is the time interval between the two events, which is star A and star B, at the same point in space. So you're measuring the time here, which is inside the space shuttle. Even though your space shuttle has moved, the clock remains at the same point in space. It is inside the shuttle. So the question repeating again, in which frame will measure the proper time? It is the shuttle's own frame will measure the proper time. A space-time diagram shows this Earth frame with word line of a spaceship S moving away from Earth, CT prime 0 when CT is 0. That means the origin of both moving frame and stationary frame overlaps at time 0. First question, determine the speed of the spaceship relative to the Earth. So we can use the value of theta here to determine the value of speed, which is tan theta is equals to V over C. That implies V is equals to C times tan theta. And what is tan theta? It is opposite, which is, let me consider this length, which is 4.2 kilometers divided by adjacent. That's the adjacent, which is 7 kilometer. And if you simplify this, the value will be 0.6c. 0.6c. Next, a flash of light sent by an Earth observer at CT equals 2 kilometers is directed towards a spaceship. So you can see that the light is sent when time is 2 kilometer, right? This from here, the light is sent towards a spaceship. Estimate using space-time diagram the time in seconds when the flash of light reaches the spaceship according to the Earth observer. So first of all, whenever a photon is sent out, the first thing that you want to do is, without even thinking further, is draw a world line for the photon, which is at an angle 45 degrees. So I'm going to take a ruler here, set the angle to 45 degrees. And from CT equals 2 kilometers, I'm going to draw a world line at an angle 45 degrees, which is going to be a world line of a photon. So that's my world line of a photon. Clear? Next. So as you can see, the world line intersects the spacecraft at this point. So that's the point where photon reaches. So this is the point where photon left the Earth, and this is the point where photon reaches the spacecraft. Now, the question was estimate using space-time diagram the time in seconds when the flash of lights reaches the spaceship according to the Earth observer. So from this, we can identify that a CT is about 5 kilometers from the Earth axis, right? That's about 5 kilometers as per the Earth axis. So T will be 5 kilometer divided by C, right? So plug in the value of C, which is 3 times 10 power of 8 will give us the value of time period in seconds. That's 1.7 times 10 to the power of minus 5 seconds. Next, determine the time coordinate CT prime when the flash of light reaches the spaceship according to an observer at rest in the spaceship. So basically they're asking you what is the time coordinate CT prime with respect to the moving frame. So I'm going to use the Lorentz transformation equation, that is CT prime equals gamma times CT minus Vx over C. So since we have already calculated the value of gamma above, which was okay, we have not calculated, so we have to calculate separately, which is going to be 1 divided by 1 minus v square over c square. So let me use the calculator. Yeah, so that gives you 1.25. So that's 1.25 times the value of CT directly. So what is the value of CT of the light reaching the spacecraft, which is 5 kilometers. So that's 5 kilometer minus, what's the value of V? The speed of the spacecraft, that is calculated as 0.6c in the first bit, times the distance. From the graph, we know it traveled a distance of 3 kilometers from the Earth frame. So that's 3 kilometer divided by the value of C. This gets cancelled. And if you simplify this, the value of CT prime will be 4 kilometer. The space-time diagram shows the axis of inertial reference frame S and the axis of second inertial reference frame S prime that moves related to S with speed this much. So value of V is given, which can help you to find the value of gamma. Let us calculate and keep it ready. So that is gamma equals 1 by root over of 1 minus V square over C square. So plug in the value of V as 0.745C will give you the value of gamma to be about 1.5. Next, event E has a coordinate x equals to 1, CT is equals to 0. So this is the event E here, and its coordinate is given here. Show that in frame S prime, the space coordinate and the time coordinate is this. So this is the value of X prime, and CT prime is what you have to show. So I'm going to use our Lorentz transformation, that is X prime equals gamma times X minus VT. The value of gamma is being calculated 1.5. The value of X is 1 minus V, which is 0.745 C times the value of T is 0. So that gives you is 1.5 meters. Next, CT prime, which is given by CT prime equals gamma times CT minus Vx over C. So gamma is again 1.5. The value as CT is 0 minus the value V 0.745 C times X 1 over C. Substituting this and calculating will give you negative 1.1 meter. Next, label on the diagram the space coordinate underline. When they say space coordinate means on the X prime frame. Label this event with letter P. So I wanted to locate this event E on X prime, which is my X axis of S prime. I've drawn a parallel line to my Y axis of S prime. So I'm going to draw a parallel line to my Y axis, right? As you can see, this line and this line is parallel, and the point where the line intersect my X prime frame is my coordinate P should be labeled. Next, label on the diagram the event that has a coordinate X prime equals 1 meter and CT prime equals 0 meter. Label this event with the letter Q. Now, so we know that the P is representing a space value as 1.5 meter, and we wanted X prime to be 1.0 meter. So what we're going to do is we're going to take a ruler and measure the length. How much is this length in centimeter, which is representing 1.5 meter? Then we'll see how much length is required for 1 meter. Okay, so before that, let me use a protractor to see how much angle is it making approximately. It is making an angle of about 36 degrees, right? So let me set this ruler to an angle 36 degrees and measure the length. So P is about 7, right? So 7 centimeter is representing 1.5 meter. Then 1 centimeter would represent 1.5 meter by 7. But the question is not 1 centimeter length of the ruler, but 1 meter on space. So if 1.5 meter is 7 centimeter as per the ruler length, then 1 meter on x-axis will be how much centimeter? We'll do unitary method, which is 7 divided by 1.5, which gives you about 4.7. So we'll see where is 4.7 centimeter. That's over there, right? So let me keep the ruler a little bit aside. Yeah, so that's the point over here. And we'll label that as Q, which is representing the X coordinate as 1 meter. Okay, representing X coordinate as 1 meter. Next, a rod at rest in frame S has a proper length of 1 meter, proper length L naught 1 meter. At time t0, the left hand end of the rod is at x is equal to 0. So that's the left end of the rod. And the right hand end is at 1 meter. So that's the right end. And that's your rod. Okay. The rod is resting on this line. Now, using the space-time diagram outlined without calculation, Y observer in frame S prime measures the length of the rod to be less than 1 meter. Now, first of all, the observer who is in space or the observer who is moving. So with respect to the moving observer, because he cannot measure the proper length, since he is moving with a speed close to the speed of light, he will end up, seeing the shorter length. But yes, he will make sure that he measures both the ends of the rod at the same time, right? I mean, because since he is moving, he cannot measure the first end and the last end at a different time interval since he's moving away. So he has to measure both ends of the rod at the same time. Now, keeping this in mind, that he has to measure both ends of the rod at the same time, that means if he is measuring the first end at this CT time period, he has to measure the other at the same CT time period. If you're measuring at this CT time period, one end of the rod, he has to measure the other end at the same time period. If you measure the first end at this CT time period, the other end has to measure at the same CT time period. That means if you see the possible coordinates is going to be giving you a word line, right? It is going to give you a word line which is going to be perpendicular to your uh, time axis, right? Now, the intersection point, this parallel line, this vertical line that you've drawn from the event E, the point where it intersects the x prime axis is where you are going to get the other end, because initial length is obviously at the origin, the other end will be the point of intersection. Now, as you can see, the 1 meter is at Q, right? The 1 meter as per the x prime length is at Q, but the ends of the rod is shorter than the 1 meter. And therefore, from the space-time diagram, we can say that yes, the length of the rod is shorter than the 1 meter. Next question. Using the space-time diagram, estimate the length of the rod in S prime frame. So you have to just find out this length. Let me label this as AB. You have to find this length AB. So I'm going to take the ruler. The same thing you will do it in the exam, right? So I remember it was 36 degrees. Yeah. And we'll measure what is the length of that AB, which is about 3.3 centimeter as per the ruler. So yeah. So that length of the rod as per the S prime is 3.3 centimeter. But since we know that 1 centimeter is equal to 1.5 meter divided by 7, then 3.3 centimeter will be 1.5 meter divided by 7 times 3.3. So if you solve this, you're going to get about 0.76 meter as the length of that rod.